Using the state assigned table, we can come up with the circuit to detect the sequence 0, 1, 0. So let's see how that is done. Now remember, we are going to construct the circuit using D flip-flops because D flip-flops are some of the most simplest of the flip-flops. And you have a reset and you have a clock. Okay, remember that the current state of the flip-flop is Q and the next state of a D flip-flop is sitting right here, but that is T. So after a clock pulse, D moves to Q. So your next state becomes your current state after one clock pulse. So this is how we do it. We are going to require two D flip-flops because we have 2 bits in our current state and in our next state. So it requires only 2 flip-flops. Now the current state, this is going to be QB, QA. Next state, remember I told you that the next state is sitting at in D. Therefore this is DB, DA, DB, DA. And you have the output Z. So basically we have to come up with equations for DA, DB and Z. So let's try to come up with the equation for DA. So if you look at this table here, you're going to see that DA is asserted only when x is equals to 0. So I can simply write DA equals x prime. Let's look at DB. DB is asserted over here, and over here. To find the equation for DB, you can either write it manually. So I can write DB equals x times QB prime QA, or x times QB QA, or x prime times QB QA prime. Or you can also use a K-map. So let's try to use a K-map. X QB QA 0, 0, 0, 1, 1, 1, 1, 0 and 0, 1. So this is for DB. DB is asserted when x is equals to 0, QB equals to 1 and QA equals to 0. So 0, 1, 0. Next it is asserted for x equals to 1, QB equals to 0, QA equals to 1. So that's 1, 0, 1. And finally, it is also asserted when x is 1, QA is 1 and QB is 1. So that's 1, 1, 1. So I can simplify this as, I can group these two together, and that would be QB prime QA, or I can group these two, which is going to be x times QA. So you can write it explicitly or you can use K-maps. So using K-maps, you don't need to worry about the Boolean algebra. You can directly come up with the minimal equation. So that's the equation for DB. And finally, Z is asserted when QA equals to 1 and QB equals to 1. So I can write Z equals QA QB. Now using the three equations, we can try to come up with the circuit. So remember, DA equals x prime, DB equals QB prime QA, or x and QA, and Z equals QA QB. So the circuit is going to look as follows. We have two flip-flops. This is D flip-flop A, and we have D flip-flop B. So this is going to be DB, QB, QB prime, DA, QA, QA prime. Both have a clock and a reset. So clock signal is fed into both these ports. Same thing with reset. Reset is fed into this port and it is fed into this port here. So dA is x prime. So I can take x as my input, knot it, and send it to dA. dB is QB prime QA. So that's QB prime and QA. I'm going to AND this, or X and QA. So this is QA, this is X. I'm going to AND it, and I'm going to OR this with this one here. And that's going to go to dB. So to dB, which is all the way here. And then I have Z, which is QA QB. So Z, which is QA QB. So I'm going to say this as QA, this as QB, and AND them together and produce Z. So this is the whole circuit diagram. It can get messy, but it is what it is.